Hi everybody, I am Mustapha Sadouki, Professor, Researcher and Director of the Acoustics and Civil Engineering Laboratory at Queen's Millennium University, HASSINE. This work, entitled Acoustics Measurement of the Failure Resistivity of Rigid Porous Materials via Low Frequency Transmitted Waves Frequency Approach, was prepared in collaboration with my two students, Nassima and Hanane HASSINE. This work is supported by the University Training Research Project (PRFE) and by the General Directorate of Scientific Research and Technological Development (DGRSTD). The outline of this work are as follows. First, general description of the porous medium is given. Then we define the biot theory and the equivalent fluid theory, which are two models describing the propagation of sound in the porous medium. In third part, the direct problem is treated, where two expressions of transmission coefficient will be given in the low frequency domain. The experimental setup will be described in the fourth part. Then we'll proceed to the resolution of the inverse problem. And we finish with conclusion and perspective. Porous materials is medium containing pores filled with fluid, liquid or gas. The skeletal part is usually solid. Many natural and made mediums such as rocks, soils, bones, plastic foams, fibrous materials, cements, and ceramics can be considered as porous materials. Among these materials, such as plastic foams and fibers, are frequently used in the automotive and aeronautical industries and in the building trade to reduce noise and vibration pollution. Therefore, good acoustic performance is desirable attribute in almost all types of buildings and is particularly important for residential buildings, schools, and hospitals. The effectiveness of these porous materials in sound absorption is mainly based on their intrinsic properties. In the acoustics of porous materials, we distinguish two situations according to whether the frame is moving or not. In the first case, the dynamics of movement due to the conflict between the solid skeleton and the fluid is well described by biot theory. In the second case, the structure is generally immobile and the waves propagate only in the fluid. This case is described by the equivalent model, which is a particular case of biot theory. In the case of porous media with rigid structure, the model of the equivalent fluid theory is used. The equation of acoustics in the free fluid are written as follows. The first is the Euler equation and the second is the constitutive equation. Within the framework of the equivalent fluid theory, the interaction between the fluid and the structure are taken into account in the two frequency response factors. The dynamic tortuosity of the medium, alpha of omega, proposed by Johnson and Dole, and the dynamic compressibility of the fluid given by Aller. In the frequency domain, these factors are multiplied by the density of the fluid and its compressibility respectively, and they represent the deviation of the behavior of the fluid as the frequency changes. There are several acoustic parameters describing porous media. These parameters can be divided in two categories: high frequency parameters and low frequency parameters. Porosity is the key parameter informing us about the proportion of fluid in the porous material. It presents the ratio of the volume occupied by the fluid to the total volume occupied by the medium. According to the Johnson-Champon-Aller models, the high frequency parameters are the high limit frequency of tortuosity and the viscous and thermal characteristic length. The low frequency parameters are the initial factors alpha 0 introduced by noise and the viscous and thermal permeability. To differentiate between high and low frequency regime, the viscous and thermal light thickness are compared at a given frequency with the effective radius of the pore. The low frequency range is defined when the viscous and thermal skin thickness are greater relatively to the pore radius. Otherwise, is the high frequency range. In the dusty regime, flow without any surf effects corresponding to the very low frequencies, the air flow resistivity is the most important parameter describing the viscous losses caused by fluid structure exchanges. In this case, the dynamic vorticity alpha of omega and the dynamic compressibility beta of omega are given by equation 1 and 2. In this equation, G is the imaginary part, phi is the porosity, sigma is the flow resistivity, rho is the saturating fluid density, and gamma is the adiabatic constant. After to this presentation of the equivalent fluid theory and biot theory as well as the definition of the different acoustic parameters, we will now proceed to the study of the direct problem. Let's consider the rigid porous medium with the thickness L. Using the condition continuity of the pressure and velocity fields at the boundary of the medium, we found the expression of the transmission coefficient T1 at low frequency. In addition to frequency, the expression T1 also depends on porosity and flow resistivity. At that regime, very low frequency, and by taking into account only the first term of the Taylor series development, expression T1 of the transmission coefficient is much simpler. It's given by equation 4. This expression T2 is independent of frequency and porosity and depends only on the flow resistivity sigma. The transmission coefficient T1 depends on the frequency, the porosity, and the flow resistivity. Sensitivity study of porosity and resistivity on the transmission coefficient T1 is presented. The table 1 shows the relative variation of the transmission coefficient T1 corresponding to variation of 20% of the porosity and the resistivity of porous medium at different frequency. According to table 1, it can be seen that the sensitivity of the porosity on the transmitted signal is negligible at very low frequency, and that the sensitivity increases with frequency, while the sensitivity of the resistivity is important at very low frequency. The second expression of the transmission coefficient established at very low frequencies is the expression T2 given by equation 4. The advantage of this expression is that it's independent of the frequency and depends only on the flow resistivity. From table 2, we can see that the influence of resistivity on the transmitted signals is important at very low frequency and that this sensitivity remains constant as the frequency increases because the expression of the transmission coefficient considered is independent of frequency. Based on this sensitivity study, we conclude that the flow resistivity has high sensitivity on the transmitted signal at low frequency and that this sensitivity is remarkable for both expression of the transmission coefficient T1 and T. At very low frequencies, the sensitivity of the porosity on the transmitted signals given by T1 is negligible, and this sensitivity increases with frequency. It's therefore preferable to use the expression T2 to characterize the porous medium in the very low frequency range, because this expression has the advantage of being independent of frequency and porosity and depends only on the flow resistivity. The simulated transmitted signals are obtained by the product of the HASSINE signal and the transmission coefficient. In the time domain, the transmitted signals is obtained by taking the inverse Fourier transform. Figure 2 shows the simulated incident and transmitted signals of porous medium constructed in frequency domain via expression 5 and in time domain via equation 6. Whose characteristics, porosity, flow resistivity, and thickness are as follows. The signals are constructed at center frequency with peaks of 100 Hz, 500 Hz, and 1000 Hz. Experiments are performed in kit pit. The chip length is adapted according to the frequency range desired. The experimental incident signals is measured by putting a total reflector in the same position as the porous sample. The experimental signals are amplified and filtered using dual column filter. The direct problem consists in constructing theoretically the transmitted signal knowing the incident signal and the parameters of the medium. Given the experimental incident signal and the transmission coefficient which play the role of transfer function of the medium as function of the parameter to be found, we deduce the simulated transmitted signal which must be compared to the experimental transmitted signal. The inverse problem therefore consists in minimizing the difference between the experimental and simulated signals by varying the recurrent parameter. The solution corresponds to the sets of parameters that give the minimum deviation between the simulated transmitted signal and the experimental one. The two study samples are industrial plastic foam M1 and M2 of thickness L1 equal 5 cm and L2 equal 2.5 cm. The physical properties of these two foams measured by direct methods are given in Table 1. Figures 3 and 4 show the spectrum of the incident signals and the experimental transmitted signals of the two foams at frequencies 50 Hz, 500 Hz, and 1000 Hz. After solving the inverse problem, it can be noted that the optimized values of the flow resistivity obtained by the two expressions T1 and T2 are identical at very low frequency. Whereas slight difference is noted between the two inverted values of the flow resistivity using the two expressions T1 and T2 for the frequency 500 Hz. However, in all cases, the resistivity values is close to the values obtained by the direct method presented in Table 1. Figures 5 and 6 give the minimization curve U as function of sigma for the two foams M1 and M2. Figures 7 and 8 show the curves of the transmitted signals reconstructed using the optimized parameters of the flow resistivity with respect of the corresponding experimental signals. From these figures, a good agreement is observed between theory and experiments. Conclusion: the important result has been obtained by using the simplified expression of the transmission coefficient at very low frequency. It's now possible to measure with very low frequency acoustic waves the flow resistivity or viscostatic permeability of porous medium without knowing its porosity or any other physical parameter beforehand. The advantage of the expression is its simplicity since it does not depend on frequency and its stability over a wide range of very low frequency, making the resolution of the inverse problem simple, fast, and efficient. Our next future work is to generalize the application of this method to various other porous materials such as fibrous and granular media.